Attention is at the core of transformer-based models, be it models like BERT, GPT, or any of it. GPT here stands for Generative Pre-trained Transformer. Transformers were mainly introduced for language translation tasks. But now it is used for a variety of tasks. Like GPT, for example, is really good at generating text. So what the model gets really good at is predicting the next word. In our previous example, we talked about an example of translating an English sentence into a Hindi sentence. We saw how we have an encoder and we have a decoder and we have a certain context in the middle. So from the English sentence, we use the encoder to convert it into a middle representation, or the context. And using the context, the decoder is able to generate the Hindi sentence. So this context is some sort of an understanding of the original English sentence. In the previous video, we saw that we first feed the input into the model and we also add some sort of a personal information along with it. Now we'll be mainly looking at this encoder block. And you can also see that there are n encoder blocks here. And it is better shown in this figure where there is the input fed, which we've covered already. And there are these encoder blocks. And then you get the context or the input embedding. Don't worry about all of these terminologies in specific. We'll get to those in detail. Right now we've seen that there are these many encoder blocks and there is this multi-head attention block. Let's first look into this. We previously took this simple sentence, the cat is on the mat, and we established that each of these words or tokens is represented by a particular matrix and has a lot of values. Earlier, we took around 20 or 50 dimensions, but for the sake of this explanation, let's say that there is around 512 dimensions to it. And by this, I mean that each of these tokens are represented by a series of numbers. Let's say the word the or even cat is all represented by a series of numbers. Maybe like this is 1.5, 6, 2, -1, etc. And then the is also represented by like 2, -1, 5, etc. And then it goes. And each of these is 512 in length. And we can probably represent this word using one number, but that wouldn't give a very rich meaning. So using these 512 dimensions, now we are at the liberty of using several combinations of this to create some meanings. Let's say, for example, the third dimension over here, let's say if this is named from 1 to 512, the third dimension over here might give an idea that, okay, this is a noun, or maybe some other number over here might say that it is an animal, or maybe that it is an object. So these numbers can give small amount of information over there. And also, let's say if we later on go to say that we have an orange cat, then maybe some of these values can change in the representation of cat so that a meaning of an orange cat is set to the idea of the cat. So basically we have around 512 dimensions just so that we have enough space to give a lot of meaning to each of these words. Let's say if we take a longer sentence for our current example, and you should also keep in mind that each of these tokens are 512 in length. And you must also notice that we have two tokens over here, x7 and x12, and it is necessary to feed into the model these tokens in between as well, maybe like end of sentence, start, stop, etc. The reason I took another additional sentence is to illustrate the following. Let's say if we take this word it comes after this particular sentence we took previously, but this it has a meaning associated with it. It here means the cat, and it in general might have a certain meaning associated with it. It as a word, if you take it directly, has a certain embedding, like it has a 512 dimensional embedding associated with it. But we need these embedding to actually reflect the meaning of cat in this particular context at least. And for a translation task, it would really help, like if the context has the understanding of the word it in this particular sentence as the cat, or even if you're using a next word prediction, for example, if we have these words it is, and then you're predicting the next word, we must have an understanding that it means the cat so that we can attach a verb over here, which is like stretching. Also note that there are 512 dimensions in this. So if we just maybe feed it to a particular neural network and then make it predict, like if we feed this word and then just let it update it to a particular value so that it refers to the cat, that is not really possible. If it is a simple problem, let's say if you have a target and just two dimensions associated with it, it has the x and the y axis, and then you hit an arrow over here, and then you can just adjust, okay, maybe change the x towards the left and towards y towards the bottom, and then you can slowly increase it, and then you can converge to this point where you have it exactly. And this is very easy because you can just slowly keep reducing the x so that the distance maybe from the origin to these points is the least. So you have a metric over here to measure it. But if we just try to change all of these 512 values, that won't be possible to make it into a certain meaning, especially something which is like associated with the cat. So it is very difficult to just use any kind of neural network to do this. So we do a series of transformations so that we can capture as much detail as possible using all of these 512 values. Since we have this 512 dimensional vector, we want it such that this represents the exact meaning in a very context-rich manner. We can imagine any word, let's say if you take cat or it, to have a lot of features. Maybe it can be said as a noun or a verb. We can decide between that. We can decide if it is a singular or a plural. We can say if it is an animal or not animal. And you can keep on going. There can be a lot of ways to decide this. So we don't want just one neural network to decide all of this together. Rather, what we do is we use something called attention heads. So there are several attention heads which focus on a particular feature. And please note that these features which I said is just taken arbitrarily. It doesn't mean that each of the attention head in a real model specifically sees if it is a noun or a verb. Rather, it just focuses on a certain feature which we won't be able to exactly say what it does. But you can understand that it might be doing something similar to this. It need not be exactly detecting whether it might be an animal or not. Maybe some of the attention heads together is doing that. But the takeaway here is that there are several attention heads focusing on different features of the input. So in our case, since there is around 512 dimensions, and in the original transformer paper, we have 8 attention heads. And each of these attention heads attend to different aspects of a single word. So the first thing we do with the input embedding, also please note that all of these input embeddings also has the positional value which is added to it. So even though we input all of this in parallel, that means that unlike the RNN model, all of these words are fed into the transformer model in parallel. Since we have this additional positional encoding, that would in turn help the model to differentiate between, okay, this is the first word and this is the last word, and things, and the exact position of one word in relation to other. And that is done using this positional encoding. So we have the input embedding, which includes the positional encoding right now. And a first step using this is to project it to a different space. That may be a bit difficult to grasp, so let me give you a few analogies to help you with. So let's say if you have an apple in the real world, there may be several features associated with it in the real world. Let's say it would have its weight, which is, let's say, around 250 grams. It might have its specific shape, and that is not even a particular circle, it is like a very different shape. And then it has other features like, let's say, the number of leaves in it and the shape of its seeds. And there are a lot of these features. And it can also have the specific color. Let's say it's not particularly red, but rather it has an RGB value of, let's say, 250, 47, something like that. It's not a real red, but rather it is towards some other color. It's like maroonish or some other color. There's a lot of features like this. And in order to exactly represent the apple, you will need so many of these features. But do we need all of these features, like the exact color of the apple pinpointing, to understand that is an apple? We don't need it, right? We might need very simple things. Is it red or not? Or like if we have the approximate shape of it, if it is shaped like this, it might probably be an apple. So we might need just a few of these, let's say 3 of these characteristics. If it's sweet or not, how it tastes, like, and if it's sour, and if it grows on a tree. There are several simple answers we can take to understand the context of this, that this is an apple. But in reality, there might be so much information associated with this apple, including its shape, its taste, its color, and so on. Just like that, in order to understand a specific context, we don't need to entirely understand the word as is in the real world, but rather we need to understand specific features of it. We need to extract specific features from it. Each of these attention heads do that particular task. So we have 512 dimensions, right? So what we do is we divide it 512 divided by 8, which is the number of attention heads. We have 8 different heads. You can imagine that each of these heads are focusing on certain features. And by 512 divided by 8, you get 64. So what we'll do is take this 512 dimensional vector and then put it into a different space entirely. And this space would help you capture some meaning of these words. That might be a bit confusing at first, but I assure you you'll get an idea of it once we complete this particular section. So let's say initially we were in a 512 dimensional space. I'll explain that to you. Right now I'm only showing you 2 dimensions. This is the first dimension, which is the x-axis, and this is the second dimension, which is the y-axis. If I put any point, you have 2, like the x component of it and the y component of it. So if I add another axis over here, now it just becomes 3 axis, and I can have a component over here as well that would just in turn transform this point to that. So you have a 3-dimensional representation. And if you keep on expanding like that and you reach 512, this becomes a 512 dimensional space. It is difficult to visualize on a 2D area. Just understand it, it allows you to encode more and more information. So when we project it to a 64-dimensional space, I'll tell you what projection means here as well. Let's say if you have this tree, and to exactly understand this, we need 3 dimensions, how the branches go, etc. Let's take the smallest branch, let's say the bottommost branch over here. If you take the 2D picture, you can see that the branch goes from here and then it goes towards a bottom angle. And this is the angle you can find here. But at the same time, if you rotate it, you can see that it almost goes in a right angle. Likewise, if you take the projection of it, if you draw a tree, then if you take a projection of it from an angle, you can probably draw it like this and it branches. But maybe in the 3-dimensional representation, and if you take it from another angle, you can probably see it go to another angle. Like it depends on your own perspective, right? But at the same time, you can clearly say other things like at what height does the first branch occur, or how many branches are there, and like at what distance does each of these branching occurs. That can be said using the 2-dimensional representation of the tree. We do not need the entire 3-dimensional representation. So what we see in the 2D plane is just the 2D projection of the tree. Likewise, we take the 512 dimensional vector and we project it to this 64-dimensional space. And let me show you the mathematics of how we do that. Even though here I've represented this vertically, let me just write it down as a list. So this becomes a 1 into 512 dimensional vector. So let's say it has a lot of values like 1.5, 1, 0.5, 6, etc. and it goes. And this is 512 dimensional. And let me remind you that this transformation is not just occurring to one word, it will occur to all of these words, and that is happening in parallel. I'm just taking one particular example over here, but all of the other words are also undergoing the same change. So we took this representation, now we need to multiply it by another matrix which is 512 into 64. This is because you must know that if you have a matrix which is 1 into 512 and you multiply it with another matrix which is 512 into 64, the resulting matrix, you'll get a 1 into 64 dimensional matrix. And this is what we require because we have initially a 1 into 512 dimensional vector. Let me just call this the input vector. And then, instead of, let's say this is the vector which is x8. Let me just call it x8. And then we need to output this particular vector, which for now we will just call as q8. And this can be represented in the space also, which is 64 dimensional. And we should also take the other word, which is cat, and we want to see how cat is related to it, right? So if we do a similar transformation like this, maybe we use another 512 into 64 matrix and we do that transformation, and then we project it to the space again, and then maybe cat goes to a particular different spot in this 64 dimensional space. And what our goal here is that this cat would be quite close to it if you're looking for similarity in this particular attention head. Maybe if you were looking for all the nouns, maybe all the nouns should point to the same spot in the 64 dimensional vector. What we just need to make the neural network learn is to make all of these align in the same direction. If this particular feature we're looking for is that, let's say if we're looking for focusing all of these words towards the cat, maybe these has to be pointing towards the same direction. Maybe if it is detecting if the word is an animal, maybe all of these animals should point towards one direction in the 64 dimensional space, and all the other words should probably be facing some other direction. And keep in mind, this is just a two-dimensional representation. When we take 64 dimensions, that means that some of these numbers would be same. And let's say if this is the first vector and this is the second vector, and some of these dimensions are same, but some of these dimensions are might be different. And we need maximum similarity between these two. We'll see how we compute that. And since we established that, we need to calculate this. And we are using the network to project it to this space. This matrix is something which is not very arbitrary. This is something we'll need the network to train on so that it projects it according to what we want. Maybe we want to project all the cats to one spot, and this is completely dependent on all of these parameters. And if you're a bit confused by now with all of these matrices and parameters, just stay with me. It'll all make sense in a moment. So this first matrix, we call it as the weight matrix of the query, like the query weight matrix. And like we said, it has 512 rows and 64 columns. And this would be WQ11, and this would be WQ512 by 64. So this would be the element which is, and this is the first matrix which we will make the neural network learn, because we need to make this projection into this space. Now we've been calling all of these vectors random names, and we've been saying this space for this. Let's give it some names. So over here, I've used Q because in the paper, they use the term query to name this vector. And the second matrix, which is similar to this, outputs the key, which is also 64 dimensional. And the reason they use the terms query and key is because this first vector, let's say Q, which is it, acts as the query, and this cat in turn is the key. Let's say this is key 2 because it's associated with the token 2. And understand that all of these words undergo this query transformation, and all of these words undergo the key transformation. So each of these tokens is associated with one key, just like key 1, and like one query, which is query 1. Let's just take this example for now, which is the second query, which is cat over here. And it over here is query vector 8. And how did we obtain the query vector 8? Just to revisit, we multiplied the word it using the query matrix, which is learned. And we transformed the 512 dimensional representation, which is the input representation we fed into the model, and we got a 1 into 64 query vector. And that is which is represented over here, which is the query vector. And likewise, we have a query and key matrix. Let's not worry about the key or query vectors for all the other words right now. We'll just look at this simple example. Since all of these words are processed in parallel, it is similar for all of these words. So we are taking the word cat and the key vector of it. And that is obtained by multiplying the representation of cat over here, which is 512 dimensional, using this key matrix. And then we obtain this key 2, which we have represented over here. So ideally, if you want it and cat to be similar, we want it to point towards the same spot in this query key space, or it has to be quite similar in this space. If it's just a simple 2D space, we can just say that it is pointing towards the same direction. Or maybe if it is a one-dimensional space, we don't want like cat to be at one end and query to be at one end. Rather, we want both of them at a similar spot. If it's a two-dimensional space, it has to be similar in that way. And if it's a three-dimensional space, we want it similar in a 3D space. But this is a 64-dimensional space, and some of these values have to be similar. And that is done by these query and key matrices. But another important thing to note is that this query and key matrix for a particular attention head. We have 8 attention heads over here, and for one attention head, let's just say we are taking H1 over here, and for that, this query and key matrix is the same. Of course, it is learned as we progress through the model, but all of these words are multiplied using the same query and key matrices. And each of these words, let's say the is multiplied with this query matrix, and you get a projection for that over here. And for the second query also you get one. And for all of the keys, you get separate projections to the space. If the idea of query and key isn't clear to you yet, I'll just explain it to you once more. So each of these words, let's say it is multiplied with the query matrix and the key matrix separately. And then you obtain one query matrix. Let's say if it is the word it, that is the 8th. So you get Q8 as well as key 8. And why do we need key 8? That is because the other word, let's say stretching or like ease, can be the query, right? There can be X9. That means there is also Q9. There is a query vector associated with it. So when it's saying is, so what is doing something? They might need to know the answer to that. So when this query is asked, maybe it can be associated with that. And it is not necessary that a particular attention head is exactly looking for that. What is the noun preceding this verb or something like that? Rather, it can be completely anything. Basically, we have a query from a word and we see the similarity in the query key space. And by the way, this is called the query key space because both of these are 64 dimensional, query and key. And please note that the 64 is just an arbitrary number we used here, and that is used in the original transformer paper. Each of the query and key is 64 dimensional because we have a 512 dimensional vector and we divided it by 8 attention heads and we obtain 64. It just seemed to work well with this model. But at the same time, let's say GPT might use a query key space which is 128 dimensional. But the principle remains the same. Now, if we remove the clutter, we saw that we have 12 inputs, x1, x2, going until x12. And then we have all the associated query vectors with it. It's q1, q2, etc. until q12. And we have all the key values as well. We have the key vectors from key 1, key 2, etc. up to key 12. And as I said before, all of these have a length of 512 and all of these have a length of 64. This is because we have projected it to the queries key space and it is low dimensional compared to the original embedding space. You can think of this as, let's say, if there is an object in the real world which has a lot of features to it, but maybe to remember it, you only have a certain feature of it. Let's say if you saw a person who was wearing a blue shirt walking around and had specs, and somebody else might have also seen them, we might just remember them as a person walking with a blue shirt and a particular feature. We don't remember every aspect of them. That's just a lower dimensional representation of them in our head. I have been mentioning that we need to find the similarity between two vectors, be it one of the Q vectors and one of the key vectors. Let's say this is the query key space, which is 64 dimensional. And then we have one query vector and one key vector. And to find how similar these two vectors are, there is a simple way to do that, and that is using a dot product. Another added advantage is that a dot product is easy to compute using programming. So let's say we have a query vector, let's say which was the 8th query vector, which meant it, which was associated with it. And we have a series of 64 values for that. Likewise, we have a key vector, which is key 2, which is the word cat. And that also has a series of 64 numbers to represent that. And likewise, for all the other words, we have a separate representation like that, which is 64 in length. So when we talk about the attention, which this word it is paying to this word cat, what we take is we take the dot product of Q with the transpose of the key. Though previously I showed you the multiplication between one query vector and one key vector, rather to get the attention scores of from one query vector, we multiply to all of these key vectors. Like we have all of these values. It means that when you're calculating the attention from this particular word to all of the keywords, we get a particular distribution here. So the problem right now is that these values may be very large or negative or any of that. It can be, let's say this was 1, this might be 300. This might be like 10, anything like that. It could keep going like that, but we will need something which is normalized. It is not easy for the model to figure it out if we just give a very large number like that. So what we do is we use the softmax function. Let's say from the table above, we give the attention scores of a particular query matrix. Let's say the query was 8, and then we get particular attention scores associated with it. Let's say it was 1, 300, 5, 6, etc. It goes like that until the last key value, which is like the 12th one. Now, what the softmax does in effect. And by the way, we have an entire video about softmax in depth in our channel if you want to learn more about softmax. But I'll give you a simple idea here. This function is something. Let me draw the graph for you. Is the output, and the x values can range from minus infinity to infinity. The y value over here, the bottom value which is being saturated is 0 and the top value here is 1. So what it effectively does, it could take a large value, maybe like infinity. If you give the value of infinity, then you would get 1. And if you give minus infinity, then you might get 0. And this is also true for very large values. Let's say we have a value which is 300. And if we have that, that might also be very close to 1. And maybe we have a very small value that might get closer to 0. So the main idea of this function is that all of these values, if you like add it up, like if we have some normalized values for all of this, and maybe this is 0.8, maybe this is 0.05, something like that. And then once you add all of these values, you would get the total as 1. So it is like a weight, as in which of these attention scores take the most weight out of 1. And with this normalization, we can clearly see which value is most important over here. And all of the other values which are not relevant gets drowned out. All right, now we have the normalized attention scores. And now would be a great time to visit the attention formula as said in the original paper. It says the attention of query, key, and value. And we have talked about query and key, but we have yet not touched the value matrix or the value vector, but we'll get to that, is equal to softmax of. Softmax is the same function we just talked about, which is used for this normalization between 0 and 1 of query key transpose. And this is exactly what we were talking about above in the dot product. Just give you the initial attention scores divided by the square root of dk. And dk over here is something we will look into first. But let me also complete the formula into v. So what we have to look over here is this dk and v. dk is just for scaling, and it is not that important to the formula. But what it effectively does is, if you have very large values and then we are sending that to the softmax, as a preliminary step, we just divide it by the square root of dk, and that is the dimension of the key matrix. We know that the key and the query matrix, and dk here is the square root of the key query space, or the dimensions. And we know that it is 64 as we have taken in this. And the square root of 64 gives you 8. So all of these values, the attention scores which we calculated, are first divided by 8. And then the softmax is applied. And this just helps in the numerical stability. Just that instead of having the values range from here, we'll just reduce it so that this function becomes much more easier to work with. And since we did the dot product of two 64-dimensional vectors, the values may be very large. And then by dividing it by the square root of dk, so we have already established that we got the attention scores of each of the query vectors. And we have an attention matrix of that form. Now let's also take the initial word, since we need to get the value matrix, and I need to show you where it comes from. And as we know, this is 512 dimensional. And we have the input token here, and this can be any input token. We am taking this as an example, and which is 512 dimensional. And I already told you that this is projected to the query space and the key space. And this is done by a multiplication with this weight matrix and also another weight matrix for the keys. Likewise, we do another transformation, and this gives you another vector, which is the value vector. And we have an associated matrix, which is the value matrix over here. And this is required because we initially projected this and we multiplied the query and key. We took the dot product and we found a similarity between something. And now we need to find what updation we need to do. And that is done using this matrix. So the exact values of the weight matrix is also learned with the training of the model. And that decides where you're transforming this initial word embedding to. So when you do the multiplication, you get Q1, K1, V1, also Q1, K2, V2. So you have queries on the top and keys here. And each of these keys has an associated value vector also. So you take the dot product and then you multiply it with the value so that that gets transformed. And this is dependent on how much attention scores it has. As in, if it is a very low score, then the transformation is scaled down by that much. Likewise, we get Q1, K3, V3, etc. And likewise, we get for the second query vector, we get Q2, K1, V1, and we get Q2, K2, V2, etc. So that for each of these key vectors, we have the corresponding value vector. And once you do this multiplication, what you get is the attention matrix. And also remember that this attention matrix is just for one attention head. Let's say this is for H1. And also note that over here, I have mentioned just for one word, but rather the value matrix, since we have the attention scores for all of these together, and even previously when we were talking about these multiplications, we were taking one word at a time, but all of these are happening in parallel. So instead of directly just taking one word and multiplying it, when we view it, it might be a multiplication with the sequence length of 12. As in, we are multiplying all of these 12 words at the same time with the value matrix. But this still holds when we look at one channel, or like if we just look at one token, how that path travels in this multiplication, that is the same. But it just happens for all the other tokens at the same time. The dimensions of the value weight matrix would be the same. It would have, let's say initially we have 12 into 512. And that would be our input. We have the input and then we multiply it by a matrix, which is the value weight matrix, which is 512 into 64. 64 is the same dk. And this is dm, is the dimensionality of each of these tokens. Keys, queries, and values all have the same dimensions in this, and this is 64. And when we multiply this 12 into 512 with this 512 into 64, we get a 12 into 64 matrix. So all of these matrices are 12 by 64. And each of these is the output of each of the attention heads, right? This is from H1, this is from H2, from H3, H4, H5, H6, H7, H8. Now we've obtained all of these values, which we multiplied from the attention scores with the value matrix. And then we have these values. Now what we do is concatenate all of these outputs. So we get an output matrix, which is 512 in length in 12. Because all of these 64 into 8, which gives you 512. And we have an entirely long matrix like that. And let's just call this the Z matrix. And this is the output of a multi-head attention. You must also notice that this is the same dimensional space as the input embedding. We had a sequence of like 12 words, which was X1, X2 through to X12. And then each of these had 512 dimensions to it. And this is the same dimensions as the input embedding. And each of these attention heads has tried to extract some features from the input embedding by transforming it to the query key space. And then we are concatenating all of that. And also, after getting the attention scores, we multiplied to the value metrics. That means we were figuring out what changes we have to make to those words in specific. And even now, we have all of these values, but we don't know what to do with this exactly. And each of these is a single head of attention. Now we have obtained this big matrix from the multi-head attention by applying the above formula of attention. Now let's see where we reached in the original architecture. So in our previous videos, we already talked about the input embedding and we added the positional embedding here. And then now we've talked about this multi-head attention. And as you can see, all of these splits over here, in turn, is the key, query, and values. And that is the split we do here. This is a query, key, and value. Since that is transformed or like projected from the input embedding itself, that is what is being fed into the multi-head attention, and we got the output here. And you can see that in much more clarity over here, where we feed in all of these value, key, and query, and then we have the scaled dot project attention. And this is like h, and we have h is equal to 8 for our case. And then we concatenate all of that, and then we got this multi-headed attention. And one thing which is remaining is this linear layer and also this additional and normalization. We will talk about the linear layer next. So even though we have all of these values, we don't know exactly what to do with it and what kind of an update we have to do. Just understand that we have this input over here and our output is something which we have set our eyes on, and that is, let's say, the Hindi translation or like the language translation of what we inputted here. And that is just in the case of this translational model. And it can be maybe predicting what the next word is. It can be anything like predicting the missing word, maybe filling the blank. A transformer can do any of these actions. Even though we understood what words to pay attention to and we've extracted some features, we don't know what to do with it. But we haven't exactly told what the model has to do with this. So from this as an input, and we have this, which is like multiplied with the value metrics, and we have the attention and it is scaled, and we understand what kind of changes this attention is suggesting. And from there, we multiply it with a simple linear layer. And by linear, we mean that it is a simple neural network. We have one layer and then we have a ReLU activation in between. We also have another linear layer here. You can imagine this as a simple, easy to train neural network as part of that. That is the linear layer. It has no other complications. It's just simple forward paths and backward paths with a ReLU in between. And it is okay if you don't completely understand how this would result in a translation. That we will look into in our next video.